Here we have 2 kilograms of oxygen filling a cylinder of a piston cylinder assembly, so it's shown right here. The initial volume and pressure are given, and there's heat transfer to the oxygen occurring at a constant temperature until the volume is doubled. So we have some heat transfer coming in, and the volume doubles, so there's some work being done on the surroundings. And we're asked to determine the heat transfer for the process, and kinetic and potential energy effects can be ignored. So we're going to make the oxygen our system. I'm going to apply the first law to that system because we're trying to find the heat transfer, and I can see here that we're trying to solve for the heat transfer. We have some work being done. There's going to be some change in internal energy here because the initial state and the final state are different. So this is really involves the first law. So let's write that down. First law for the system is change in total energy of the system is equal to the energy going into the system via heat transfer minus the work leaving the system because we're doing work on the system's doing work on the surroundings. So let's go ahead and evaluate what these various terms are. So the change in total energy of the system is going to be the change in internal energy plus the change in kinetic energy plus the change in potential energy of the system. But we're told that the kinetic energy and potential energy aren't changing for the system. These are good assumptions because there's no velocity change in our system, and the system's not changing its elevation, so it's not changing the potential energy. So no velocity change means there's no change in kinetic energy. No elevation change means no potential energy change. So we're just left with the change in internal energy. I'm going to drop the subscript system here just for convenience. So now to get the change in the internal energy, I'm just going to expand that out into the mass of the oxygen multiplied by the change in specific internal energy, which will just be the mass times the final specific internal energy minus the initial specific internal energy. Okay, let's go ahead and continue. The heat transfer into our system, that's a question mark. We're trying to solve for that, so we don't know the answer to that just yet. The work done by the system on the surroundings, well, this is P dV work. So this will be the integral of P times dV, that's the volume. So we go from some initial volume to some final volume. Let me write that instead of volume, let me write it in terms of specific volume. So if I do it in terms of specific volume, I'll just multiply this by mass. So then I have pressure times d little v. So we go from some initial specific volume to some final specific volume. Now the pressure, we're told in the process, remains constant. So we're told that it's a constant pressure process here. So let's pull the pressure then outside of the integral. So it's just integral dV. So that just means that the work done by the system on the surroundings will be the mass times the constant pressure times the final specific volume minus the initial specific volume. So let's go ahead and substitute these back into our first law expression. So on the left-hand side I have mass times U2 minus U1. The right-hand side I have Q into minus mass times pressure times V2 minus V1. Okay, so this is what we have from our first law expression. Now if I look at that for a moment, I'll see that I have some internal energies and pressure times specific volumes. This looks like specific enthalpies. So in fact, if I combine those together, you'll see if I bring them to the same side, I'll have Q into is equal to the mass times U2 plus PV2 minus U1 plus PV1. And so you can see these are in fact specific enthalpies. It just makes the problem a little bit easier to work it out in terms of specific enthalpies rather than having to work it out in terms of specific internal energies and specific volumes. You could certainly work out, find what the heat transfer is here using the pressure, specific volumes, and specific internal energies. No problem, you can do that. Or it's just a little cleaner if you work it out in terms of specific enthalpies like what I have here. It's just a little easier to work with, I think. You don't have to do this way, but it's easier. Now, The mass of the oxygen, we're told in the problem statement, mass is 2 kilograms. So I'll just make a note here, mass of the oxygen is 2 kilograms. Now to get the specific enthalpies, to find those I'm going to look them up in a ideal gas table for oxygen. It's the most accurate way to do that. But in order to do that, remember that for an ideal gas, the specific enthalpy is a function only of temperature. So I need to know what the temperatures are at the initial and final states. So to find, and if you go back to the problem statement, you'll see in the problem statement we're not given the temperatures. We're given the volume and pressure, but not the temperature. But that's okay. We can find the temperatures from the ideal gas law. We're going to assume that the oxygen is an ideal gas. Note that so far we haven't actually assumed that the oxygen is an ideal gas anywhere in this analysis. All we've done so far is just apply the first law and then just use the definition of the specific enthalpy here. That's all we've done. We haven't said that we're dealing with an ideal gas yet. So I'll just make a note here. Just assume O2 is an ideal gas. So now we're making the assumption that the oxygen is an ideal gas, so we'll make use of the ideal gas law that says the pressure times the volume is equal to the mass times the gas constant times the temperature, so we can rearrange that to get temperature. And we know the initial pressure and the final pressure, they're the same. Those are 1 bar. It's an absolute pressure that we're given. We know this initial volume was, that initial volume was 2 cubic meters. And then the final volume, we're told it doubles. So the final volume is 4 cubic meters. And then, by the way, I made a mistake here when I wrote out the ideal gas law. This should have been T is equal to PV all over MR. I had written it incorrectly. Okay, and then the mass we're told was 2 kilograms. Now to get the gas constant, remember this is the gas constant for oxygen. It's not the universal gas constant. It's not the gas constant for air. It's the gas constant for oxygen. To find that, you can look that up in a table. And if you do that, you'll find that it comes out to be 259.83 joules per kilogram Kelvin. So this comes from a table. It's just if you look in the back a lot of textbooks for properties of ideal gases, you'll find this gas constant for oxygen. Another way you could find it is you could take the universal gas constant and then divide that by the molecular weight of oxygen. That's another way you could do it. And the molecular weight of oxygen is, you can go to the periodic table. We call it molecular weight. It's also known as a molecular mass. But you could look that up in the periodic table, what the molecular mass of oxygen is, multiplied by 2, because we're dealing with oxygen gas here, which is just O2. And that'll be 31.999 kilograms per kilomole. And then the universal gas constant, you can look that up. I don't have it handy right now, but you could find that also from a table. So that's how you could find the gas constant for oxygen as an alternate method. But anyway, we have the gas constant for oxygen looked up, so we can find the temperatures. So we'll find T2 comes out to be 769.73 Kelvin, and T1 is 384.86 Kelvin. So now that we have those temperatures, we can find the specific enthalpies. So specific enthalpy at 1 would just be the specific enthalpy at T1. And we can look that up in the table. So I've copied parts of the relevant tables. So this is an ideal gas table, ideal gas properties table. For oxygen. And you'll see that, for a temperature of 384 Kelvin, it's going to be somewhere between these two temperatures, right? So we're going to have to do a linear interpolation to find what that specific enthalpy is. Note that that specific enthalpy is in kilojoules per kilomole. Okay, so just be careful of that. If you do that linear interpolation, then what we get is that this value comes out to be 11,260.01 kilojoules per kilomole. You can do the same thing for the final state. That's at temperature T2. Again, going back to the table, you'll see that it's temperature of 769 Kelvin, somewhere between those two. So you'll have to do some linear interpolation. It'll be awfully close to this value at 770 Kelvin. But if you do that linear interpolation, this one comes out to be 23,507.09 kilojoules per kilomole. Now again, these are in kilojoules per kilomole, so if you want to find them in kilojoules per kilogram, what you do is you divide this by the molecular mass, which we gave over here. So take that 11,260, divide by the 31.999, and then that will give you the specific enthalpies in terms of kilojoules per kilogram. So H1 then would become 351.89 kilojoules per kilogram, and H2 is 734.62 kilojoules per kilogram. And just to, again, I'll just put a reminder here. If you want H1 in kilojoules per kilogram, that'll be H1 in kilojoules per kilomole divided by the molecular weight. That's how we found that. Okay, so now that we have the specific enthalpies here, we can plug them back in up into this relation and calculate what the Q into is. And if you go through that calculation, then the heat transfer into the oxygen comes out to be 765 kilojoules. All right. So this is the method using the ideal gas tables, where we looked up these values for the specific enthalpies. Now another way we could approach it would be to say, okay, starting from here, let's assume that the oxygen is a perfect gas. What I mean by a perfect gas is that the oxygen is not only an ideal gas, but an ideal gas with constant specific heat. Remember that these tables here take into account that the oxygen has a variable specific heat. The specific heat varies with temperature. For a perfect gas, we would assume that it doesn't vary with temperature, so we wouldn't use these tables. Instead, what we would say is that for a perfect gas, Cp is equal to a constant, and so the H2 minus H1 would just be Cp times T2 minus T1. Okay? So then our Q into would be mass times Cp times T2 minus T1, assuming that we're dealing with a perfect gas where the specific heat's a constant. Now, we know the mass, we know the temperatures. The temperatures we found just right up here using the ideal gas law. So that leaves finding the specific heat at constant pressure. So there again, what you can do is use a table to look that up. And, in general, the Cp is a function of temperature. So you might ask yourself, well, what temperature should I use? So what I did is I just used a temperature somewhere between these two values, just kind of an average type of temperature. So I looked it up in a table, Cp for oxygen at T equals 600 Kelvin, so somewhere in between those. When I looked that value up, it came out to be 1.003 kilojoules per kilogram Kelvin. Right? It's just this C sub P, since I'm assuming it's a constant, I just found a temperature that seemed to be sort of reasonable between those two temperatures. In fact, the C sub P varies from 384 Kelvin to 769, so I just tried to use kind of an average value in between them, and that's what I got. This comes from a table. Actually, it was an online table that I used. But now that I have that, I can calculate the Q into in that case. And the value I get when I use this approach is 772 kilojoules. So you can see, by assuming that I'm dealing with a perfect gas, I don't get quite the same value as the more accurate approach using the ideal gas tables, but it's not too far off. In fact, if you look at the percent difference, so if I do percent difference, that's just the Q using the perfect gas assumption minus the Q ideal gas approach divided by Q ideal. So it's like when you do a percent difference, it's the less accurate approach minus the kind of quote-unquote correct approach divided by the correct approach here. So if I calculate that percent difference, it comes out to be less than 1%. Okay, actually this is, you'd have to multiply this by 100%. And what you'll find is it's less than 1%. So using the perfect gas assumption here is not that bad. It's a decent assumption. You know, so if we did that perfect gas assumption, we get 772. It's pretty close to the more accurate approach of using the tables. I wanted to show using the tables here because it's really the most accurate approach to make use of these ideal gas tables. So this is the most accurate value. This is a pretty good approximation, assuming that we're dealing with a perfect gas. Okay, we'll end the example there.